electrically large loops. Or you can also call this resonant loops. Loops that are so big that they have enough self-capacitance to resonate out their self-inductance. Now, what does an example of this type of loop look like? I'm going to start by looking at the square loop. And for the square loop, I'm going to have current circulating around in this direction, keeping in mind we're talking about sinusoidal current. So 0 degrees, the current's rushing in this way. If I wait half of a period, 1 over 2f, later in time, it will go back the other way. I just happen to be showing you the reference. It's phase equal to 0. Now, in fact, I've drawn this a little bit wrong because the same technique that we use to calculate the standing waves for dipole antennas. Remember at the beginning of the class we had open circuited transmission lines. We figured out what the standing wave pattern would be and we bent them back. We could do the exact same thing here, but it's going to take a little bit of imagination. Let's say I have a transmission line that is short-circuited, right? Because I have a path, electrical path of conductor all the way around. I short-circuit the path. Now my current is going to be at a maximum here, and the standing wave is going to proceed like this, where this is going to be a quarter wavelength from the end. And I have the exact same pattern, of course, down here. Quarter wavelength. This is a half wavelength. And this polarity of current is going through here, down through here. And then I get polarity reversals when I traverse the null. That's just back to the very first week of class, very first couple weeks when we reviewed transmission lines, standing waves, came up with the solutions. We've been doing this all class period long. The only difference is that I shorted this instead of opened it. So that means I'm at a peak instead of a null at the end. Now, for my resonant loop, this is all going to be a quarter wavelength in every dimension. It's going to be a square. And the total electrical length is going to be 1 wavelength. So this is actually going to be 1/8 of a wavelength on this side of the feed, and 1/8 of a wavelength on this side of the feed. And if this is my transmission line, my center point that I really bend around that corresponds electrically to this point on my short circuit is on both sides a half a wavelength around. So if I go a half a wavelength around here, I'm actually right in the middle of this peak. So this is the section that I need to bend around my square loop. Well, conveniently, here at the end, remember that corresponds to this point, I have a peak. I have a really nice peak. I've got an 1/8 of a wavelength on either side that constitute this quarter wavelength section of wire that I bend out. So it's not a full hump of sinusoidal current, but it's the biggest central part of the current. And according to this diagram, it's going to be going this way. Start from that point and then adjust our conventions relative to the end that we've discussed. Okay, now when I get to the sides here, I got to go another half of a wavelength. So I'm in a quarter of a wavelength, excuse me. But this is 1/8. I need another 1/8 to get to a full quarter of a wavelength. So what I've drawn between these two here are the sides. What I've drawn here, here, top, and the bottom of the loop. Can everybody see that? Can everybody kind of bend it with their mind? Are you getting used to these problems enough where you can do that? I was telling my advanced analytical EMAG class today, senior level or a PhD level course, we were reviewing our residue calculus. Anybody ever study residue calculus in your undergraduate curriculum? No? It used to be required when I was a student. In my day, we had to go to class every day, carrying steel I-beams uphill both ways, learning residue calculus. Jeremy?
Is that related to the residue?
What do they call the residue method in your math class? So is it contour integration in the complex plane?
Yeah.
Yeah, that's it. The Cauchy theorem, when it says if you do an analytic function, you do closed integral in the complex plane, you always get 0, unless there's little poles in there. Yeah, good. What class did you learn that? All my students in the other class that were from Georgia Tech as an undergraduate looked at me as if I had grown a third eye in the middle of my head.
I didn't.
Okay, what class is that? Oh, yeah, good class. That encourages me. Yeah, so the whole point I was making with them, I was trying to explain them this residue theorem. And I was drawing on the board, and I was like, oh man, it's hard to draw on the board because I think I need 4-dimensional paper. I have the complex plane, which is your argument, and then the function would also itself be complex in many instances, and so I need 2 dimensions for the input, 2 dimensions for the output. I can't draw that on the board. And I was told them, I think the real value of taking electromagnetics classes is that you go to the conceptual mind gym, right? And like no other course will you be tested in your mind for visualization ability, your ability to bend the world around into something that makes sense. And I often think that maybe that more than anything else that you learn in an electromagnetics course will serve you better than the actual knowledge itself. Having been to this weird mind gym, you will be able to conceptualize so many interesting problems when you get out into the world, some of them having nothing to do with electromagnetics. Anyway, that's just a theory, untestable. I've not figured out a way to test that theory yet. Okay, so we have this situation where I've got the big peak here, and then through here, I have my inflection currents. They start at a low amplitude, they cross 0, and they end up at a similarly low amplitude. And this, by continuity, would have to bend around this way, but there's an inflection, so you've got the current this way, and the same thing happens over here. Draw this in the middle, inflection in the middle, little amplitudes this way, and then a reversal halfway through the other way. And then this guy over here looks the same way. He's got a big peak through here, and the current should all be in the same direction. And lo and behold, because it's reversed itself, it's actually pointing in the same direction as that top current. Can everybody visualize that? Sorry, I don't know if you can see. This doesn't have one of those lower features. Anyway. Really complicated down here. A bit lower. It does. I'll try to draw high. So what happens here is that, well, let me ask you, which direction does this thing radiate in? I've got a couple different alternatives. Let me draw a coordinate system first so we can talk about it. Z is coming out of the board, X is in this direction, Y is in this direction. So first, tell me about the Y direction. In the Y direction, partially, because this is lambda over 4 out of phase with that, right? So it's not going to be complete destructive interference, but it's not going to be full constructive interference either. This is when you send a wave, when this radiates to here, they're radiating in phase, but when this one gets to this point, the wave from here gets to this point, it's 90 degrees out of phase, which is kind of like 6 in one hand, half dozen the other. It's adding to it a little bit, but it's not like it's aligned. So you're right, this will radiate in this direction pretty well, and you get some partial constructive interference in this direction. So, make a little chart. Why? Good. Z. What happens in the Z direction? Yeah, but by themselves, these are kind of like weird dipoles where you've chopped off the little tail currents. So they're radiating omnidirectionally with a big current mass. Probably looks almost like an ideal dipole. And then you have an exact one down here that's in phase. So in this direction, positive Z as well as negative Z, they're going to constructively interfere. I'm going to put Z better. X. What about X? Worse, better. But yeah, go with your gut, man. Yeah, it's going to be a very deep null. It is both the inflection point and also the fact that you have mirror image current. It's not going to be completely destructive because they're only a quarter wavelength apart. But it's the mirror image currents this direction. So this polarization in Z is not going to make any contributions in this polarization because they're the opposite phase and they have an inflection point. So this cancels with this cancels with this, and if there was any residual, this would cancel with this. This is one of the marvelous things about loop antennas. People use them often in direction finding. You say, how can you use a loop antenna to find direction? It has the world's crummiest half-power beamwidth. We're not talking about a very large antenna. You're probably lucky to get 90 degrees of half-power beamwidth out of this antenna. However, if you are trying to find, let's say you take a vertically polarized source like this, you hook up your little receiver and your little headphones and you listen to the beacon transmit. Take your loop antenna and use it in this configuration. You hold it out and you're trying to listen to vertical polarization. These won't contribute because they're horizontal, right? Aim your deep null towards that source. You shouldn't hear it. If you take this deep null and you tilt the antenna just a little bit to the left or a little bit to the right, the source will pop up again. So it gives you a technique for doing direction finding with what is typically considered to be a electrically small and kind of fat-lobed antenna with very little half-power beamwidth. If you were trying to point the peak in the direction of the desired source and listen to it, and just try to direction find that way, you wouldn't be able to do it because you wouldn't hardly, your hearing is logarithmic. You wouldn't be able to hardly see much signal change as you swept the peak gain along the horizon. And trust me, as soon as you introduce some multipath fading, you're not going to be able to do anything. But if you steer this null towards the source, and remember your receiver usually has like 60, 70, 80 dB of dynamic range, move a little to the right, move a little to the left. All of a sudden, your signal jumps up 20 dB, becomes detectable again, and you can slowly triangulate where your beacon is using this type of antenna. Now, see, deep nulls have a purpose sometimes for some antennas. But you would really, if you wanted outright coverage with your loop antenna, you would like to use it in this configuration, where the horizontal, or however you've oriented field would be horizontal the way I've drawn it on the board here, and the peak gain would be this direction, you would still get some gain. So it'd be kind of like that, the way I have it here, the elevation cut of my phi hat electric field would be like an oval if I did a cut like this. Maximum, minimum but not a null, maximum, minimum but not a null. And then I also, you get very similar behavior if you try a lambda circular antenna. It behaves very similar. And I think for show and tell last class period, I brought in a little loop antenna that was electrically large and that it had 360 around here, but then had capacitive breaks, bring it down a little bit more, confine the current a little bit more. There's a lot of really interesting games you can play with antennas, loop antennas, even though they're fundamentally very simple. Do a lot of interesting things with them. Jared?
So a 3D pattern would look like a donut?
Yeah, that's right. So it would be an oval, and then you would definitely have nulls in these two directions. So it's almost like a electrically short dipole with the sine squared pattern, except turn it on its end, turn it on the side. So the nulls are in this way, the donuts in this way, and then take this dimension and go about 50%. Very good mind jam, visualization jam. Okay. So, typically around 1 lambda, these things are almost purely real. Reactive component dies away. Sometimes you got to add 10% to the length to make that happen because there's some interactions along here that make it less than ideal. But if you do that, the impedance is usually around, not too far from 80 ohms, almost like a dipole. What's interesting about the loop antenna, the electrically large loop, is that there are repeated resonances, really almost just like a dipole antenna that you keep adding half wavelengths to get bigger and bigger. So for example, you can make a 2 lambda loop, which looks very funky. Might even have you do a homework problem. But that also resonates again. The reactive component collapses. You get a large real value. And according to Stutzman, that real value is closer to 200 ohms, or higher, over twice what the 1 wavelength loop is. And you can keep on enlarging it. Of course, you have to realize that as you keep enlarging it, you're increasing the resistance, series resistance. You could be lowering the radiation efficiency. You usually are lowering the radiation efficiency. You're also making the design a little bit more temperamental and sensitive to perturbations. If you add if you are 5% off in your length of an electrically small loop, it hurts you a lot less than if you're 5% off in the circumference of a 1 lambda loop, which hurts you less than if you're 5% off in a 2 lambda or 3 lambda. There's also a mechanical stability issue you get with these planar antennas. You make them out of wire, but they're kind of saggy, right? They don't behave like the way you think unless you have some sort of translucent or something that is translucent to RF to kind of prop it up. Piece of cardboard, piece of wood, poster board from your store. That stuff is basically invisible to RF if you ever need to build an antenna and mechanically stabilize it. Okay. Any questions so far? Okay. Well, if there's no questions, I'm going to move on to the next topic. I need to check with the people from home. Okay, good. No questions. Not good that there's no questions, but good that I did not miss any questions.